Welcome back to the final main session of the day, and we'll directly jump into it with our first presenter, Alain Lefebvre. Alain is a graduate from ISAE ENSMA Mechanics and Aeronautics Engineering School in Poitiers. He has a PhD on professional thesis of mechanics, energetics, aerodynamics, and thermics at the Toulouse University. He was previously expert in fluid system simulations at Renault Powertrain Division and worked at Renault Technical Center in Ladi up until 2022. He's now system architecture expert at Safran Tech in the aerospace industry, and he's going to talk a little bit about GT Suite at Safran Tech for the study of zero-emission aircrafts and propulsion systems. Alain, the stage is yours.
Okay, thank you, Ian, for this kind introduction. So I'm going to present you the use of GT Suite at Safran Tech for the study of zero-emission aircraft and propulsion systems. So first, the agenda of this presentation. So I will do a short overview of Safran Group and especially Safran Tech. Then I will remind you the objectives of the aeronautic industry in terms of CO2 emissions. Then I will explain why we have decided to test GT Suite in a proof of concept since June 2023. I will focus on the fuel cell application example. And finally, I will give my conclusions on perspectives. So, Safran Group is well known for its aircraft and helicopter engines, you know, probably CFM 56 or LEAP family. But Safran is also present in many fields of aviation, space, and defense. It's a problem. Okay. So Safran is a French group with 41,000 employees in the country and 75 sites in France. But it's also an international group with 276 locations in 27 countries and more than 83,000 employees. So Safran Tech now. So Safran Tech is the group's research and technology center. So it's located in the south of Paris, on the Paris-Saclay innovative site, and is very close to Versailles. Safran Tech is also present in Toulouse area, where Safran has many sites linked to the aeronautics industry. So Safran Tech represents 25% of the research and technologies of the group, and with 20 nationalities, 500 employees, 100 experts, and about 300 patents per year. So the three main activities are material and process, energetic, and information. So now the objectives for aeronautics. So due to global warming, decarbonizing aeronautics is a key driver for coming years. Aviation only represents 2% of the emissions, of the global emissions, but the aircraft fleet should nearly double by 2040. So different objectives have been taken, so minus 30% in greenhouse gas emission by 2025 and minus 50% in 2050 compared to 2005. So to reach this objective, SAF, so for sustainable aviation fuels, should be used quickly, but it will be also necessary to optimize current technologies and to develop H2 based new technologies. Sorry. Okay. So Safran is already strongly involved in decarbonization. You have different examples. You have the RISE engine on the left, which is an open fan engine. Safran also supports the introduction of SAF and is developing electric propulsion on hybrid aircraft. So now the GT suit modeling. So in June 2023, we decided to start a proof of concept to test GT suit. So hydrogen mobility was chosen for the study. Hydrogen as a combustion fuel, but also hydrogen as a fuel for the fuel cell. So different topics have been chosen. So fuel cell modeling, cryogenic and two-phase hydrogen, heat exchangers, cooling, and thermal management systems. I'm going to focus on the fuel cell application now. So the question is it possible to have an aircraft with a fuel cell? So it's a feasibility study. So is it possible to replace a classical turboprop system by a fuel cell-based system? Is it possible to keep nacelle dimensions? So the case study is 19 passengers commuter aircraft with a cruise speed of 100 meters per second, a cruise altitude of 10,000 feet, a mass of about 6,800 kilograms. The propulsion system is a PMFC low temperature, so about 70 degrees. The power is higher than 500 kilowatts per engine, and we use a water cooling system. So as you know, different GT models are available for the fuel cells. So the first level is polarization curves, so it's a zero-D approach. The second level is a more detailed model based on geometrical parameters and physical characteristics. And the third level would be CAD data with GEM3D and physical characteristics that we didn't test at the moment. So we used level 1 and level 2 at the moment. So the cooling issues. As you imagine, when you have 500 kilowatts per engine with a fuel cell efficiency of about 50%, the main issue is the cooling, because you have similar heat transfer rates. So about 500 kilowatts and more. So the issues are quite similar to the automotive industry that you know, but with a stronger mass on aerodynamics coupling. Because when you increase the mass, you need to increase the lift to compensate, and then you increase the induced drag due to the relationship between the lift and the drag with the polar curve. So the mass is very important, and the cooling is also very important. So we decided to test heat exchangers template models available in GT Suite. So we mainly used tube fin types with external fins. We used DOEs, latent cubic DOEs, to reduce the number of cases, so about 350 cases. And we used standard conditions for the takeoff phase. We imposed ramp velocity at 0 altitude with standard atmospheric conditions. And we tested different geometrical parameters in the DOE. It's very easy with GT to have the results on response surfaces. You have here the outlet temperature of the coolant from the fuel cell as a function of different parameters. So you have the fin density, the fin pitch, the number of rows, the number of heat exchanger tubes, and you have our limit of 70 degrees. The heat exchanger mass is a direct output of the DOE, so it's very easy to build a meta model, for example, by Kriging, and to do a direct parametric optimization under constraints by, for example, imposing the outlet fuel cell temperature to 70 degrees, minimizing the mass, and also the drag due to the pressure loss of the system. You have here the results of the simulations, and you have the effect as an output of GT simulations, the effect of the most influent parameters on the results. You have here the effect on the fuel cell outlet temperature. So once the cooling system has been sized for steady-state conditions, it's possible to simulate now transient conditions. So for this, we have modeled the full system. So it's based on the new examples available in GT 2023, where there is an aircraft model. So we use the aircraft from the aircraft, to the propulsion system, where we have 2 fuel cells, 2 e-motors here. Okay. And we perform transient simulations on a mission profile. Everything is controlled by the flight controller, and the wing aerodynamics coefficients are calculated in this part. And everything is calculated as a function of operating conditions on altitude. We also included the calculation of the induced drag due to heat exchangers pressure losses, as we have seen before. So drag and thrust are calculated thanks to the control libraries of GT by applying the Euler-Baylan equations on the heat transfer domain, as you see here. The consumer's consumptions on power are also calculated by GT. For example, the cooling pump, the compressor, the H2 pump. And it's therefore possible to get the net power from the fuel cell and the power available at each time step for the e-motors. We also added the weight force variation due to H2 consumption, to the fuel consumption. So we used for the fuel system a detailed model in order to calculate the heat sources coming from the stack. And the mass of the stack is already included in GT with a 1D thermal model. For the cooling system, it's the same. The thermal masses are already included in the templates model of GT. So everything is already available to calculate thermal inertia during the transit. So for the mission profile, we use a target of aircraft speed, which is controlled by the electrical motor torque demand. and a vertical speed target of 8 meters per second, controlled thanks to the angle of attack of the elevator. So the first result is the real longitudinal aircraft speed compared to the target. So you see that at the beginning there is a deviation compared to the target. It's too slow. By analyzing the results, in fact, we see that it's not due to the response time of the system, but to PID calibration issues. It's the same for the fuel cell response. So this question of response time is important because in aeronautics there are norms that impose a takeoff distance. So the short takeoff and landing value is necessary to avoid an obstacle at the end of the track. So the target, which was 366 meters with our first calculation, is not achieved, but it can be achieved by using more aggressive PID coefficients. These new PID coefficients causing instabilities, so we used variable PID coefficients in a timetable for the entire simulation. Now the most interesting result. So if we look at the fuel cell cooling and especially the temperature, the outlet temperature of the fuel cell. So in this case, we are at 20 degrees at ground level, and we have 20 degrees for initial stack temperature. So you see that the temperature increases. So you are in the takeoff phase here. But you see that the temperature increase is not so high. So you see that the limit under steady state condition, which is 70 degrees, is not reached. So this is the good news. And you see that it is because of at 200 seconds you are at already high altitude, 1,400 meters. So the temperature, the external temperature decreases. But at the beginning, in fact, it's due to inertia of the stack on the heat exchangers. You have about 400 kilograms of stack on heat exchangers. So there is a very big inertia, and the temperature doesn't increase so much. And the maximum temperature of the stack is respected under transient conditions. If we now consider more severe conditions, if you take 55 degrees for the initial temperature of the stack, you see that it's a little worse, but you see that due to the efficiency of our cooling system, it's possible to decrease the temperature during takeoff. So it would be a takeoff after rolling on the track when you have 55 degrees. And you have the cooling system effect. And finally, if we use quite severe conditions, so 45 degrees, it's something like Dubai conditions in the desert. You see that we have an initial temperature of 55 degrees, and you see that it's the same. You have a decrease of the temperature due to our cooling system that is sufficient to cool down the fuel cell. And the maximum temperature is respected, even with these hot conditions. So the conclusions. So the heat exchanger modeling capabilities available in GT Suite have been used. So we used DOE's optimization tools to optimize the heat exchanger size under steady state conditions. It's possible to directly optimize the best trade-off between cooling, pressure loss, drag, and mass on a fixed operating point. So the example was a takeoff phase, but you can also optimize on a set of operating points, like mixing between takeoff, climb, top of climb, cruise, descent. The full aircraft modeling has been used on the mission profile. You see that the sizing of the heat exchanger under steady state condition is still usable under transient conditions, even with severe transient conditions because of the thermal inertia and the decrease of external temperature with altitude. We have tested different initial system temperature and surrounding temperatures, and there is a large influence of the thermal inertia of the cooling performances, and the maximum temperature is respected under transient conditions. So for us, GT Suite is one of the most advanced 0D1D software for the modeling of H2-based systems, so for the fuel cell, but also for two-phase flows necessary for the simulation of hydrogen. It's a real fluid mechanics code based on 1D Navier-Stokes equations, and you can address many physical problems, so it's very interesting. We have a quick and good answer of the models under steady and transient conditions for the sizing of the system, and we have the direct component masses and their effect on the thermal inertia that is taken into account. We need to improve our simulations, for example, for the fuel cell control, as you have seen with our PIDs. We will test level 3 fuel cell models, and simulation should be compared to measurements and test results. So this is the end of my presentation. So thank you for your attention. And if you are interested, you can contact me. The aeronautic is hiring, so there are job opportunities. Thank you.